Continuing our discussion on the RF microelectronics basics or the overview. In the last video, we talked about the big picture. We talked about the different components of a transceiver and how these different these components differ from each other in terms of the requirements. We saw that the microwave designers mainly focused on passive devices. The RF circuit designers mainly worked on the active devices, but in a higher frequency range. The analog circuit designers worked on active devices in the lower frequency ranges, and in the digital circuit design part involved digital design, as it mentions, which is completely different from the analog part, the analog counterparts in the low and high frequency ranges. So this is a completely different field of work, and we'll not be talking about this. Neither would we be talking about this. Our focus for this entire course would be this section. So before we go there, we need to understand certain things, and I'm sure you understand them from your undergraduate courses or from your higher secondary education as well. We'll just try to recapitulate the different concepts which are involved in RF circuit design. We'll start with the electromagnetic spectrum, and we'll try to understand, and the key idea is to remember these bands. So these are all what we call IEEE bands. These are IEEE bands, and they have been assigned letters by IEEE. So the L band is from 1 to 2 gigahertz, the S band is from 2 to 4 gigahertz, the C band is from 4 to 8 gigahertz, the X band from 8 to 12, the KU band for 12 to 18, K band from 18 to 26, KA band from 26 to 40, so on and so forth. And as you might find in this one, the 2 to 4. So your Wi-Fi signals, which are typically 2.4 gigahertz, lie in the S band, and newer Wi-Fi signals, which are around 5 gigahertz, they lie in the C band. So going on in this course, if we are trying to design a certain circuit, we'll try to design it in one of the bands. So you should know and you should understand what these bands refer to. Or if you see a research paper, you look at the heading of the paper and it mentions an L band or an S band or a C band or a KU band power amplifier. You should understand what these different bands mean and what are the frequencies they represent. So mainly from this slide, I would like you to remember these different bands and the different frequencies they represent. Now again, so these different frequencies, now this is a very old slide, but it's still relevant. These different frequencies are allocated to different applications. Like we mentioned in the previous slide, this 2.4 gigahertz and 5 gigahertz, it's assigned to Wi-Fi. And similarly, different other frequencies, for example, KU band and KA band, they are assigned to satellite communications. And you'll find your dish TV networks, which are basically satellite networks. They rely on these bands, which have been assigned to them for mass media, for television based communications. Now so again, this mentions the different segmentation we have. So you can see GPS here, right? So GPS and Bluetooth, and again the cable TV, which is rare these days, also depends. So these are the frequencies which are assigned to cable TV. So it starts from this frequency and ends at this frequency, although this happens over wired media, then there is also frequency assigned to it. Then FM is assigned a certain frequency. Mobile radios, GSM signals, they're assigned approximately 900 megahertz. So all of these different assignments are done by a regulatory authority in each country. So the Department of Telecommunications, the TRAI, which is the Telecom Regulatory Authority of India. So Department of Telecom, TRAI. These govern the assignment of the spectra to different applications. Now, one might argue that there's not much difference between analog circuit design and RF circuit design, but they are different in many ways, and the way they are designed, the way these circuits are designed, is also different. So what I'd like to focus on is that there are a few things I'd like to focus on. There are the analog circuits, they work on baseband signals, so which, as I mentioned, are low frequency signals. But the RF circuits, which we'll talk about, they work with carrier signals, which are high frequency signals. So this is one key distinguishing factor between analog circuit design and RF circuit design. And because it's a high frequency signal, the size of components used is different. So at higher frequencies you have a smaller wavelength, which in turn makes the size of the component smaller. And RF circuit design is, again, it's very distributed in nature, so you can't as you go on higher in frequencies, you can't really use lumped components. You have to work with transmission lines or so, which is completely different from analog circuit design, where you can definitely, and you always, use lumped components. And with high frequency signals, and as well as RF circuit design, the phase of the signal itself becomes very significant. So it becomes so significant that it can drastically affect your performance. But in analog circuit design, the phase of the signal does not matter that much. The phase of your system matters. So in say in analog circuit design, signal phase is not important, but in RF circuit design, signal phase is very important. So you need to understand, and you need to be able to control signal phase when you're designing an RF circuit. You need to take that into account when designing RF circuits. Similarly, there are many things in RF circuit design which do not have any significance when designing analog circuits, like reflections. We don't care about reflections in analog circuits. In non-linearity, noise is somewhat this is debatable. Noise finds its applications in both RF and analog circuit design. Coupling is, again, something which does not happen at low frequencies. This is something which happens at very high frequencies, and again, it's something which is not done in analog circuit design. Now, this is a primer on basic physics. So again, wavelength and frequency. So wavelength is simply the distance between two crests or between two troughs of a wave, and the frequency is the number of wave crests that pass over an origin or any point in a given amount of time, say for example per second. So if it's per second, then it's hertz. If it's per microsecond, it's megahertz, so on. So then you have a very simple relation, which is c, which is the speed of light. Since we're assuming we're dealing with wireless communications, so all wireless signals, they basically travel with the speed of light, and it can be expressed as wavelength times the frequency, or so this should, let's not so this is v and not v velocity, so let's not confuse it with v. This is frequency, so c is basically lambda by t, right? If you go by the dimensions, it would be length by time. So you have a length and you have a time factor, and 1 by time is frequency, so you have lambda nu. So this is the Greek letter nu for frequency. Now these are the different frequency spectra, which are broader than what we mentioned in the previous slides. That was just the RF spectrum. This is the entire frequency spectrum, all the way from gamma rays to radios. And what we are mostly interested in is this section of the RF spectrum, of the entire electromagnetic spectrum. So this is our interest area, microwaves and radio waves. Now if we do a comparison between RF and digital circuit design, you'll see that there are a few differences in terms of how bandwidths are allocated. If you look at older designs, say for example from the 80s or 90s, you'll see that the digital circuit designs, so this is digital and this is RF. You'll see that the digital circuit designs, they started with DC. They had a bandwidth of say around 60 to 70, around 70 megahertz. So this is the old designs, and for RF they normally started high up somewhere. Even the carrier frequencies were low, say some megahertz. So at that point, it was simply RF did not exist. It was simply analog circuit design. At that point you had a narrowband system, say for example with a bandwidth of 0.2 megahertz, some kilohertz, some hundreds of kilohertz, but your carrier frequency was some megahertz. But when you move to newer systems, you will find that we would no longer be able to work with simply the analog circuit concepts, and now we are moving to carrier frequencies in the gigahertz band. And even for digital systems, we have moved to the gigahertz band, and the bandwidth in both cases has now spread out. Now, earlier it used to be a few megahertz or a few kilohertz. Now for both cases it is a few gigahertz. And as we move on, I mean this is still a bit old. The newer systems would work on greater than 2 or greater than 3 gigahertz, right? And modern processors, they touch almost 5 gigahertz, right? So we have been going up in terms of bandwidths and in terms of the center frequencies as well. And this is where the transition from analog circuit design to the RF circuit design is happening. So in this case, you can work with analog circuit design, but in this case, you'll need much more than simple analog circuit design. You'll need to consider many more things. So what are the key differences? So the key differences are So first we'll start with bandwidth. In traditional RF applications, it used to be narrowband, but high frequency. And traditional digital applications used to be wideband, but lower frequency. The center frequency used to be lower, but the signal used to be wideband. And the traditional RF applications, the center frequency used to be high, but used to be narrowband. Although this definition is no longer valid, we now have very high frequency and wideband systems which are being designed. The second is input power. Now, for RF circuit designers, input power can vary. If you're designing a PA, you can have a good input power level, right? Input power can be high. If you're designing an LNA, then you can have a low input power level. So you're designing for all different cases, and there can be a large variation in the levels of input and output power levels, in the levels of input and output power. But for digital applications, the entire basis is that you should not have any static power dissipation, and they are inherently low power devices. The entire goal of switching to digital was to minimize power dissipation, and digital designers, they switched to CMOS, right, which is the complementary logic, just because they wanted to save power. So being low power is a key aspect of digital applications. Now, the level of interconnects. In terms of digital applications, you see a very high density of interconnects, because you are designing using really millions of devices. So digital designs are very automated, and they involve many more transistors at different levels, and you'll see 6 or 7 layers of metal, and that makes it very complicated. So the density of interconnects, it goes as high as 7 or 8 layers of metal, and it makes it very high density. But for RF applications, you'll barely need 2 or 3. In very complex designs, maybe 2 or 3. But if it's a very simple design, you can work with one metal layer, and that should be sufficient. And the next thing is the circuit schematic. The circuit schematic is not that important in digital designs, because there are systems in place which don't care about how the circuit is designed. So, for example, for what I wish to say is that for digital applications, your building block is a gate, right? And the gate has a fixed circuit design. So you have a fixed, right? And it's so you have a fixed circuit design, and this design itself has been optimized, and now it's not critical. Now all you have to do is use these gates to form different components, right? But in RF applications, your circuit itself changes based on the application, which is not true for digital applications. You can have different applications, but all of them will use the same gates, will use the same elementary circuit. But for RF applications, depending on the impedance, or depending on what you're trying to drive, or depending on what kind of signal you're receiving, which you want to amplify, your circuit will change, and you'll need to make those changes every time you're designing. You can't just have a basic building block and use it wherever you want, like in digital applications. Now there's electromagnetic coupling. So what happens in RF applications is that since we're working with high frequencies, it might require you to no, not only are we working with high frequencies, we're sometimes working with high powers as well, right? So you might need to shield your device. So if this is your device, you might need to shield it. Otherwise, what will happen is that it will start leaking power. It will start leaking power, and it will start interfering with other devices. You have to make sure that it's properly, if you're working with high powers and high frequencies, you have to make sure that you have proper shielding, so that this does not leak radiation and start interfering with other products in a similar frequency band. Now this problem only emerges at high frequencies, because it is only at high frequencies that you start seeing radiation, and it also happens only at high power, because in order to radiate something through air, you need to have very high power levels. Otherwise you won't, because there's a lot of attenuation in air, and in order for a signal to reach a certain point, in order to interfere with something, you need to have a very high power level. And for digital applications, since we mentioned we're working at low power levels, these issues do not come into picture. But digital applications also need proper designing, because they depend on, they are sequential circuits, right? Digital circuits have sequential components, and timing is very important. So you have to design them properly, so that you have proper timings, and the times do not change, and that could introduce many errors in your system. Then coupling between two lines. For example, you have two different lines which are carrying data. At high frequencies, they might couple with each other, right? And this can be useful. This can also be harmful. So this can be useful in the RF domain if you want them to couple. And there are applications, and the application is called a directional coupler. And we'll see how a directional coupler is used. We'll see a very important application of a directional coupler as we move on. But in the digital domain, it's highly undesirable. You don't want two lines, you don't want them to communicate. This should not happen. This can lead to a lot of errors. And isolation. So this is something which is very common in RF domains, and this does not have a proper corresponding effect or a corresponding implication in digital domains. There's no such thing as an isolation issue in digital applications, but isolation is it is very much required in RF systems. So it is that you are able to distinguish between different frequencies, and you don't mix them up. That's not an issue with digital application, but RF applications highly depend on that. Now, why to use CMOS for RF? There are many reasons to do that. As we mentioned, there's no static power dissipation, so that is good. Even for RF, it's better if we don't have static power dissipation, although we can have active power dissipation. That's good. We will have high levels of active power dissipation. The most important factor for CMOS is the integration. So something which is in fact a good selling point for CMOS in RF design is that it is easily able to integrate with the existing silicon. So you have a digital design on a silicon chip, and if you are able to get an RF circuit design on a silicon chip as well, then you're able to do everything on a single chip. And basically, you might have heard of the term system on chip, right? So if you're able to do your RF, your analog, and your digital. If you're able to do all three on a single chip, that's good for you, because that drives down costs, that drives down complexity. You don't have to, that drives up performance because everything is closer to each other, right? Otherwise, you have to have an RF component on, say, gallium arsenide, on a gallium arsenide chip, and then it has to have long cables or long interconnects to connect it to the digital system. This interconnect can itself reduce performance. So what you want to do is you want to keep them closer together, and integration is one of the key reasons why CMOS is preferred for RF circuit design. But then it has its own limitations, and if you're trying to do a high power design or a very high frequency design, you have to move from CMOS to other technologies, and you can't really do an SoC in that case. Okay, now moving on to the question of sinusoids. You might see that we'll always talk about sinusoids when we're dealing with RF, or even with analog. We always try to deal with sinusoids, and it even for a basic signals and system course, you'll see sinusoids are being talked about a lot, and the reason for that. So if we ask ourselves this question, why are sinusoids important? And why don't we use some other form, right? Why don't we use rectangular or triangular waveforms? And the key reason we do that is twofold. One is that sinusoids can create all other waveforms, right? Because they form a complete basis. So sinusoids are, you can call them the building blocks of all other waveforms. You can create any waveform using sinusoids if you join them properly. That's what we do during Fourier transforms, right? And the second reason is that sinusoids scale linearly in LTI systems. So if you have a linear time invariant system, which we assume our systems will be, then the sinusoids just scale linearly. So what I mean to say is that when you pass a sinusoid through an LTI system, you can have one of two things. Either its amplitude can change, or there'll be a change in its phase, but it will still remain a sinusoid. That's very important. That's the beauty of sinusoid. So you can perform elementary operations on sinusoids, and then you can see the impact on other waveforms just by understanding how the system treats sinusoids. Moving on to, so we talked about a linear time invariant system. So let's talk about them in more detail. What is a linear time invariant system, and how does it impact our signals? So let's talk about linear time invariant systems. A very basic example of a linear time invariant system would be a resistor. If you have a relation where you have the voltage and current dependence of a resistor, you can see that so this is the output and this is the input, and this is your, say for example, this is your resistor. You give it some voltage, you receive some current, or sorry, the other way around. So you give it some current and you receive some voltage. Now if you scale the current, for example, you provided 2 times the current, then you expect expect 2 times the voltage because of this relation, right? So if you multiply a 2, you'll multiply a 2 here as well. So this dependence, where you scale the input and you get a scaled output, makes it a linear system. So this is a linear system. Now it's time invariant if the resistance is not a function of time. So if the resistance does not change with time, then this system is a linear time invariant system. Similarly, you can talk about a capacitor. If the capacitance is not a time dependent function, then this is a time invariant system. And again, this is a linear system because if you scale the input, which is the voltage in this case, if you scale it by say alpha, then the current is also scaled by alpha, then that makes this a linear system. Now there are components, there are devices which are not linear. For example, MOSFETs. Now MOSFET is an inherently non-linear device. So if you look at the current voltage characteristics, these are non-linear, right? If you look at the drain current with respect to the gate voltage, it's not a linear device. But if you work in a very small region of operation, you can assume it to be linear. That is what we do when we talk about small signal characteristics, right? Small signal models or small signal characteristics. In small signal models, we assume the operation to be in a very small region of bias. We assume that the applied VG is changing the change in VG is a very small quantity. Then we assume that the change in ID as well is a very small quantity, and that these relations form a linear dependence because it's a very small portion of the overall nonlinear curve. Then we can assume this MOSFET to be behaving linearly in this region of operation. So even if a device is nonlinear, we can treat it to be linear in a certain region of operation, and this is what we normally do for nonlinear devices. We treat them to be linear in certain regions of operation, and we call these models small signal models because we assume the signals to be small, and because the signals are small, we assume the systems to be linear. Now, as I mentioned before, an important property of LTI circuits is that a sinusoidal input results in a sinusoidal output. So you can characterize a system based on its sinusoidal response. How does a system respond to a certain sinusoid? That tells us a lot about that particular system. So if you have a system, if you have an LTI system and you give it a sinusoid and you look at the output sinusoid, it will have two things. The amplitude will change and the phase will change. So you can characterize this system on how it changes certain sinusoids. So how it changes the amplitude and how it changes the phase of sinusoids. That is enough to characterize the system. And as I mentioned, they maintain the general shape of a sinusoid except for a scaling in the amplitude and a shift in the phase. So these are the only two things an LTI system would do to a sinusoidal input. And that's all for LTI systems. Now, as I mentioned, the importance of sinusoidal signals over rectangular or triangular waveforms. Again, triangular or rectangular waveforms do not possess this property. So if you feed an LTI system a rectangular waveform, it may or may not provide you with a rectangular waveform at the output. Similarly, for a triangular waveform, it may or may not provide you with a triangular waveform at the output. So these signals are not they don't go through LTI system unchanged. Certainly you can't use these signals to characterize such systems. or to so these types of signals cannot be used to define LTI systems. And then if you look at the non-linearity of signals of systems, so if you have a system, if you have an LTI system and you want to see, now by inherently it's linear, but then assume you have a system which is non-linear. You want to understand the degree of non-linearity. Again, you'll use sinusoids. So what you'll do is that you'll either use one sinusoid of a single frequency, say omega naught, and you'll see how the system changes that. Say, for example, instead of omega naught, you also get omega 1 and omega 2. Then that itself helps you understand or helps you characterize the system. Or if you provide two inputs, we'll talk about these different methods in the future, to a non-linear system, then you see components which are an algebraic sum or an algebraic difference of these two at a different frequency, omega naught plus omega 1, or at a different frequency, say omega naught minus omega 1 or omega naught plus omega 1. So then again, you can characterize the system to be non-linear, because this is not linear behavior. If you provide a frequency, if you provide a signal with a frequency omega naught, a linear system will have an output at omega naught as well. But a non-linear system will have outputs at multiple frequencies. So again, sinusoids can be used to characterize non-linear systems as well. And then, as I mentioned, the third point would be that sinusoids, that any signal can be formed using sinusoids. So you can combine sinusoids of different frequencies, different amplitudes to form a single, and if you join them together, you can form any waveform, say a triangular wave, a rectangular wave, or I don't know, some particular waveform you want. You can always create any waveform using sinusoids, and once you understand the behavior of a system to sinusoids, you can then understand the behavior of the system to any waveform. So that's why sinusoids are important, because they can use to understand the transfer function of this device. They can help you understand how this device will behave when it's applied with different waveforms. Now, so before we move forward, we'll see in the RF domain, we'll talk a lot about 50 ohms. This is a number we'll encounter at a lot of places. Go back, So 50 ohms is a number we'll encounter repeatedly throughout this course. So why 50 ohms? What is 50 ohms? The reason we work with 50 ohms is that in any RF system, so for example, you have an RF system where you have an input, then you have some amplifiers, then you have an output. So this input will be supplied through some connectors. It might be an SMA connector, it might be an SMB connector, it might be a BNC connector, and then say for example this is your connector, then it will be connected through a wire, right? It will be connected through a wire. Now this wire, this may be a coaxial cable. It may be a coaxial cable, it may be a microstrip line, or it may be some other form of cable or line. Now we'll see that when we work with RF systems, we always want these cables and these lines we'll want them to be 50 ohms, to have a characteristic impedance of 50 ohms. What characteristic impedance is, we'll look at that later. But this number 50 ohms, why do we need this 50 ohms? And that is because this number was chosen as standard back in the days when we had just coaxial cables. Now, why was this chosen as a standard? Because it provided a sweet spot between loss and power handling. So if you look at how the cable loss changes with impedance, so you have increasing impedance, and this is your cable loss per meter. You'll see that there's a dip, and this dip happens at 77 ohms. So if you have a cable with a characteristic impedance of 77 ohms, you have the minimum loss in a cable. And if you have a characteristic impedance of 30 ohms, then the power handling capacity of that cable is the highest. So it can handle the highest power if it's at 30 ohms, and it has the lowest loss when it's at 77 ohms. So that's why a number between these two was selected to offer a good trade-off between loss and power handling. So a 50 ohm line is good at power handling, as well as it offsets some cable loss. It's a good compromise between the two, at least for air dielectric coaxial cables. And since then, this standard has been moved on to other forms of transmission lines, and now is a universal standard. So all measurement equipments, you'll find most of them working on a 50 ohm standard. So all of the input ports and the output ports of those measurement equipments will be 50 ohm terminated. So they will be 50 ohm impedances, and they expect that the devices which will be connected to them will be 50 ohms. So whenever we design a system, we always design so that the ends of that system, it does not matter what's in between. If we have a system, we always ensure that the impedance looking into the ends is 50 ohms. That's what we always try to do. And with this, I'll end this lecture, and then in the next lecture we'll start actually looking at the various topics which make up microelectronics. We'll look at the basics and the different components of microelectronics, the basics, the key topics that we need to understand in order to understand microelectronics. So with this, I'll end this chapter, and thank you.